Hi everyone, and welcome to our new unit. We're going to talk about the topic of rotation. So in particular, in this unit, we're going to cover, I think it's chapters 10 and 11 in your textbook. Um, so we'll start off here focusing on rotational motion. Here it says a new kind of motion, but we'll see it's not too unfamiliar. Um, we're going to focus on two things in particular today from these list of things. We're going to focus on the radian and rotational kinematics. Later on, we'll focus on torque, rotational inertia, so on and so forth. All right, so the first thing I wanted to mention is just something that I kind of breezed through last unit, and that's center of mass. So center of mass, sorry if you hear kind of noises in the background, that's my dog playing with her toy upstairs. Anyway, so center of mass is basically the average location of the mass of an object or a system of objects. Right, so here on this left-hand side, there's a picture of a barbell where the right-hand side of this barbell is more massive than the next. So the average location of the center of mass value is not going to be directly in the middle, but slightly to the right because the right-hand side has more mass than the left. One simple way you can determine kind of physically in real life the location of the center of mass, especially if the object is something like a thin rod here, is the center of mass is going to be where the balancing point of the object is. So if you're able to balance the object on a pivot or on a finger, the location of the center of mass is going to be along that vertical axis. So we'll see later on in this unit why that is. Now, something else I just want to be a little bit particular about in terms of center of mass, you might also hear the term center of gravity. For our course, these are basically the same thing. Technically, there's a difference. Center of gravity is going to be where the force of gravity acts, but for us, these two things are going to be the same. So we see here in the picture on the right that the center of mass of an object does not have to be on the object itself. It could be at a location where there's no mass at all. And we see that here with the person bending over with their arms hanging down. We see the center of mass of that person is not even in the object itself. That's also the case with something a little bit more simple like a wheel. If we just a wheel, let's say there's no spokes or anything, there's nothing inside the center of it. But the center of the location of the mass is going to be the center there. So pretty cool. So when we've been analyzing the motion of an object, we've assumed that our object doesn't have size or shape, that we've been using the particle model. What we really have been doing is analyzing the center of mass motion for an object. So we've been analyzing how the center of mass behaves and moves. Now, when we're dealing with momentum, the total momentum of a system is the system's total mass divided, Sorry, I just got confused by the fact that I spelled by incorrectly. Total mass multiplied by the velocity of the center of mass of that system. So we could compute the momentum of a system if we knew the velocity of the center of mass of that system. Right? That could be a little bit more complex, but still something we could do. Now, if we are talking about external forces acting on the system, the center of mass accelerates as if the mass of the system are all concentrated at that point. Right? If there's no net forces acting on the center of mass, then it does not accelerate. Okay, so let's now talk about translational motion and rotational motion. So different types of ways we can categorize motion. So translational motion, so here I have some sort of funky shaped object and I have a red dot at the center of mass. Translational motion means that the motion of the center of the mass of the system is going from one spot to another through space. All right, so this would be an example of translational motion. Now, rotational motion occurs when the object spins about its center of mass. All right, so the center of mass here does not move in physical space, but the object itself is moving, it's rotating. We can also have a combination of this motion, so both translational and rotation. So the object rotates while also moving from point A to point B. All right, so we've already talked extensively about translational motion. That's all the motion we've talked about so far this school year. So whether it be kinematics or how forces behave, so on and so forth. So now we're going to take into consideration what happens if the object's able to rotate as well. So let's see. I wonder if this will work. All right, so here we can trace out the trajectory of an extended object. All right, so here we see a racket, and there we go, being thrown. All right, and if we focus at the end of the handle, we see that this racket traces out this kind of funky curve here. This curve has a specific name. Don't remember what it's called. Sigmoid, maybe? I don't want to mislead you. But if we traced out the center mass motion for this object, we see that the center of mass of this racket traces out that parabolic trajectory that we expect. Ooh, this is fun. Now we see here that the handle, if we have a camera following that parabolic arc, we see that that this racket is exhibiting that circular motion. All right. So let's have some new vocabulary here for describing rotational motion. Right. So there are three rotational motion terms that we need to use. Right, and that's going to be angular displacement, angular velocity, and angular acceleration. So three terms that we're familiar with: displacement, velocity, acceleration, but we've thrown this word angular in front of it. Now, in terms of symbols, right, really what we have is angular position, theta, and angular displacement is going to be your change in that value, so delta theta. Angular velocity, we're going to use the Greek letter omega here to symbolize that. So that's what this curly W is here, Greek letter omega. And then we're going to use the Greek letter alpha to denote angular acceleration. Or you may have used alpha as a kind looks like the proportionality symbol used in mathematics. But before we kind of describe how we can use these terms, let's first talk about how we can measure angle in radians. And you might already be familiar with this from math class, but when we're dealing with the definition of a radian is through this formula here. All right, so if we have, let's say, a circle, and we're going to just look at a segment of this circle. So we have an arc length S, a radius r, and an angle s. So this angle theta, excuse me. And this angle is what the arc length kind of chunks out, what it traces. Perhaps might be a better term. We define this angle to be the ratio of the arc length divided by the radius of the circle. Now, this angle, when we do this, we're dealing with a length divided by a length. So this does not have any units, right? So when we say angle in radians, radians is not actually a unit. It's just a word that we use just to be a little bit more precise in terms of what we're talking about. So when we deal with the physics in today's lesson, we're actually going to be using angle in radians. Now, just like mathematics or math class, it's going to be convenient for us to define the counterclockwise direction to be positive. So for the most part, we're going to do that. Technically speaking, you can call clockwise positive. There's nothing wrong with that. But conventionally, we're going to say counterclockwise is positive. So here are some examples of how you can measure an angle in radians. So let's look first here to the right in a very simple situation, right? What we would normally think is a 90-degree angle, right? But that's degrees, not radians. So here our circle has a radius r, and since this is a quarter of the circumference, where circumference is 2 pi r, that means that the arc length here is just half times pi times r. So we use that arc length divided by the radius, giving us the angle being 0.5 radians. All right, so 90-degree angle is half a radian. Half pi radians, excuse me. Now we could have things not be in terms of pi, right? For example, here, if we have a radius of 5 meters and an arc length of 3 meters, then this is 0.6 radians. All right. For math class, you might be familiar with the bottom right here, where normally we'd say this is 180 degrees, right? But in terms of radian, we're dealing with now arc length of pi times r divided by the radius, giving us pi radians, right? So this means that there are 2 pi radians for one full circle. How do I pause this recording? Sorry, you guys.